As centuries passed and human civilization continued to develop, our understanding of Mercury evolved from mythological interpretation towards scientific observation. This transformation occurred gradually, shaped by brilliant minds across many cultures who turned their attention to the heavens and asked fundamental questions about the nature of celestial motion. Let us follow this thread of discovery through the ages, tracing how Mercury helped shape our understanding of the solar system itself. The astronomical traditions of ancient Greece laid crucial groundwork for later scientific developments. Greek philosophers developed sophisticated models to explain the movements of the planets, including fleet-footed Mercury. Aristotle proposed a geocentric universe, with Earth at the centre and all celestial bodies revolving around it on crystalline spheres. In this model, Mercury occupied one of the inner spheres, closest to Earth after the Moon, accounting for its rapid apparent motion. The Ptolemaic system, developed by Claudius Ptolemy in the 2nd century of the Common Era, refined this geocentric model to account for observed planetary motions with remarkable accuracy. Ptolemy's system employed a complex arrangment of circles upon circles, with planets moving on small circular paths called epicycles, while these epicycles themselves travelled along larger circular paths called deferents. This elaborate mathematical framework could predict planetary positions with sufficient accuracy for practical purposes, though it bore no relation to physical reality. For Mercury, the Ptolemaic model required particularly complex adjustments. The planet's rapid motion and its tendency to appear alternatively in morning and evening skies demanded careful mathematical treatment. Ptolemy's solutions worked reasonably well for prediction purposes, allowing astronomers to forecast Mercury's appearances for astrological and calendrical purposes. The geocentric model would dominate Western astronomy for over 1,000 years, its authority strengthened by theological interpretations that placed humanity and Earth at the centre of divine creation. During the medieval period, Islamic astronomers preserved and extended Greek astronomical knowledge, while European learning entered a period of relative decline. Scholars in Baghdad, Cairo, Cordoba, and other centres of Islamic civilization translated Greek texts, corrected errors, and made new observations. They refined the values of astronomical constants and developed improved instruments for measuring celestial positions. Their work on Mercury and other planets would later prove invaluable to European astronomers during the Renaissance. The revolution in our understanding of the solar system began with Nicholas Copernicus, the Polish astronomer who proposed a heliocentric model in his masterwork, published in 1543. Copernicus placed the Sun at the centre of the planetary system, with Earth and other planets revolving around it. In this new framework, Mercury's behaviour suddenly made more intuitive sense. Its rapid motion and its inability to stray far from the Sun in our sky naturally followed from its position as the innermost planet, orbiting closer to the Sun than Earth does. The Copernican model faced resistance on both scientific and theological grounds. It seemed to contradict common-sense observation, which suggested that Earth stood still while the heavens rotated around it. Religious authorities objected to removing Earth from the centre of creation. Yet the heliocentric model offered a more elegant explanation for various planetary phenomena, including Mercury's peculiar behaviour, and gradually gained acceptance among astronomers. Tycho Brahe, the Danish astronomer who lived in the latter half of the 16th century, compiled the most accurate observations of planetary positions yet achieved, all made with the naked eye in an era before telescopes. While Tycho developed his own compromise model of the solar system that kept Earth stationary, his meticulous observations would prove crucial for later discoveries. His data on planetary positions, including Mercury, provided the raw material from which Johannes Kepler would derive his revolutionary laws of planetary motion. Kepler, working with Tycho's observations after the Danish astronomer's death, discovered that planets do not move in perfect circles, but rather in elliptical orbits, with the Sun at one focus. This insight, published in his first law of planetary motion, fundamentally changed our understanding of celestial mechanics. Kepler's second law described how planets move faster when closer to the Sun and slower when farther away, sweeping out equal areas in equal times. His third law established a precise mathematical relationship between a planet's orbital period and its distance from the Sun. Mercury played a special role in testing and refining these new ideas about planetary motion. Its highly elliptical orbit made it an excellent subject for studying Kepler's laws. The planet's swift orbital period of approximately 88 Earth days allowed astronomers to observe multiple, complete orbits within reasonable time frames, providing numerous opportunities to check predictions against observations. The invention of the telescope in the early 17th century opened new possibilities for observing Mercury, though the planet remained challenging to study. Galileo Galilei, who turned his telescope toward the heavens and revolutionized astronomy, attempted to observe Mercury's phases. Just as he had demonstrated that Venus showed phases like the Moon, proving that Venus orbited the Sun rather than Earth, Galileo sought similar evidence from Mercury. However, Mercury's small apparent size and its proximity to the Sun made detailed observations extremely difficult. Despite these challenges, later observers did confirm that Mercury exhibits phases, waxing and waning as it orbits the Sun, just as the heliocentric model predicted. When Mercury lies on the far side of the Sun from Earth, we see its fully illuminated face, and it appears full, though very small due to its distance. As Mercury moves around its orbit and approaches the same side of the Sun as Earth, we see increasingly less of its illuminated surface until it presents a crescent shape. These phase changes provided additional evidence supporting the Copernican heliocentric model. Throughout the 17th and 18th centuries, astronomers continued refining their observations of Mercury. They tracked its transits across the face of the Sun, those rare occasions when Mercury passes directly between Earth and the Sun, appearing as a small dark dot moving across the solar disk. These transits occur approximately 13 times per century and provided valuable opportunities for precise measurements. By timing Mercury's transit from different locations on Earth, astronomers could apply geometric principles to calculate distances within the solar system. The transit of Mercury observed in 1631 was the first ever predicted in advance and successfully observed, fulfilling calculations made by Kepler before his death. This successful prediction demonstrated the power of the new mathematical astronomy to forecast celestial events with precision. Later transits allowed astronomers to refine their understanding of Mercury's orbital parameters and contributed to improving the overall scale of the solar system. Attempts to map Mercury's surface features began in the 19th century, though they proved frustrating and largely fruitless. Astronomers peering through their telescopes reported various markings on Mercury's disk, sketching what they believed were permanent surface features. However, different observers reported different features, and no consistent picture emerged. The combination of Mercury's small apparent size, its proximity to the Sun requiring observations through thick and turbulent atmosphere near the horizon, and the planet's slow rotation creating observational ambiguities all conspired against accurate mapping. One significant error that persisted for decades concerned Mercury's rotation period. In the late 19th century, the Italian astronomer Giovanni Schiaparelli concluded that Mercury rotated on its axis in the same amount of time it took to orbit the Sun, approximately 88 Earth days. This would mean Mercury kept one face perpetually toward the Sun, just as our Moon keeps one face toward Earth. This synchronous rotation seemed plausible and became the accepted scientific view for many years. The idea of a synchronously rotating Mercury captured popular imagination. Writers and scientists imagined a world divided into three zones: a burning hot day side, eternally facing the sun, a frozen night side, locked in permanent darkness, and a narrow twilight zone between them where temperatures might be moderate enough for exotic forms of life. Science fiction stories explored this imagined twilight zone, depicting strange civilizations clinging to existence in the narrow band between fire and ice. This compelling vision would eventually prove incorrect, but it persisted well into the 20th century. Only with the development of radar astronomy in the 1960s would scientists discover that Mercury's rotation period actually differs from its orbital period. The planet rotates 3 times for every 2 orbits around the Sun, creating a more complex relationship between its day and year than previously imagined. As our narrative moves toward the modern era of space exploration, we carry with us this rich history of observation and theory. Each generation of astronomers built upon the work of their predecessors, gradually constructing a more accurate picture of Mercury and its place in the solar system. The mistakes and corrections along the way remind us that science is a process of refinement, always subject to revision as new evidence emerges. Mercury has been a companion to human astronomical inquiry from the very beginning, from Babylonian clay tablets to Renaissance telescopes to modern radar installations. Its story intertwines with the broader story of how humanity came to understand the cosmos, serving as a testing ground for theories and a challenge to observers. As you rest and reflect on this history, consider how many minds across how many centuries have contemplated this same small world, each contributing something to our collective understanding. Mercury's place in our solar system. To truly appreciate Mercury, we must understand its position within the grand architecture of our solar system. This innermost world occupies a unique niche, experiencing conditions unlike any other planet orbiting our Sun. Let us explore the context in which Mercury exists, examining how its location shapes its nature and how it compares to its planetary siblings. Our solar system formed approximately 4.5 billion years ago from a vast cloud of gas and dust surrounding the young Sun. As this primordial nebula collapsed under its own gravity, it flattened into a rotating disk with the proto-Sun at its centre. Within this disk, solid particles began to stick together, gradually building larger and larger objects through a process called accretion. These growing bodies, called planetesimals, eventually became the planets we know today. The inner region of the solar system, where Mercury formed, was too warm for volatile substances like water ice to remain solid. Instead, the building blocks available in this zone consisted primarily of rocky materials and metals that could withstand the intense heat near the young Sun. This is why the 4 inner planets, Mercury, Venus, Earth and Mars, are known as the terrestrial or rocky planets. They are dense worlds composed primarily of silicate rocks and metals, in contrast to the gas giants of the outer solar system. Mercury occupies the innermost position among these terrestrial worlds, orbiting at an average distance of approximately 58 million kilometers from the Sun. To put this in perspective, Earth orbits at about 150 million kilometers from the Sun, roughly 2.5 times farther out. This proximity to our star defines nearly everything about Mercury's nature, from its extreme temperatures to its lack of substantial atmosphere to its rapid orbital motion. The Sun appears enormous from Mercury's surface, dominating the sky with an apparent size more than 3 times larger than what we see from Earth. The intensity of sunlight at Mercury is approximately 7 times greater than at Earth on average, though this varies significantly as Mercury moves between the closest and farthest points of its elliptical orbit. At perihelion, Mercury's closest approach to the Sun, it receives about 11 times the solar radiation that Earth receives, while at aphelion, its farthest point, this drops to about 4.5 times Earth's solar flux. Among the 4 terrestrial planets, Mercury is the smallest, with a diameter of approximately 4,880 kilometers. Mercury is only about 38% as wide as Earth. In fact, Mercury is smaller than 2 moons in our solar system, Jupiter's moon Ganymede and Saturn's moon Titan, both of which exceed Mercury in diameter. However, Mercury is significantly more massive than either of these moons, reflecting its dense metal-rich composition. Despite its small size, Mercury is the second densest planet in the solar system, surpassed only by Earth. When astronomers correct for the compression of internal materials caused by gravity, a factor more significant in larger planets, Mercury actually has the highest uncompressed density of any planet. This remarkable density tells us that Mercury contains an unusually large proportion of heavy elements, particularly iron, compared to the other terrestrial planets. The reason for Mercury's exceptional density has been a subject of scientific investigation and debate for many years. One possibility is that Mercury simply formed from material naturally enriched in metals due to its proximity to the Sun, where temperatures were high enough to vaporize many lighter compounds. Another hypothesis suggests that Mercury once possessed a larger rocky mantle, but lost much of it in a catastrophic collision with another large body early in solar system history. A third idea proposes that intense solar radiation during Mercury's formation stripped away lighter elements, leaving behind a metal-enriched remnant. Each of these hypotheses has strengths and weaknesses, and the true explanation may involve elements of multiple scenarios. What we know with certainty is that Mercury possesses an enormous iron core relative to its overall size. This core makes up approximately 85% of Mercury's radius, compared to about 50% for Earth. If you could slice Mercury in half, the core would dominate the view, with only a relatively thin layer of silicate mantle and crust surrounding it. Comparing Mercury to the other terrestrial planets helps us appreciate what makes this world unique. Venus, the second planet from the Sun, is nearly the same size as Earth and possesses a thick carbon dioxide atmosphere that creates a runaway greenhouse effect, making its surface the hottest in the solar system. Earth, our home, is the only planet known to support life, with liquid water on its surface and an oxygen-rich atmosphere. Mars, the fourth planet, is larger than Mercury, but smaller than Earth, with a thin atmosphere and evidence of past water activity. Mercury differs from all of these in fundamental ways. It lacks the substantial atmosphere of Venus and Earth, possessing only an extremely tenuous exosphere of atoms blasted off its surface by solar radiation and micrometeorite impacts. It has no geological activity comparable to Earth's plate tectonics or volcanic systems. Its extreme temperature variations exceed anything found on the other terrestrial planets, and its orbital characteristics, which we will explore in greater detail shortly, set it apart as a world of unusual dynamics. The relationship between Mercury and the Sun is intimate and overwhelming. Mercury orbits within what might be called the Sun's extended environment, where solar influences dominate every aspect of planetary existence. The solar wind, that continuous stream of charged particles flowing outward from the Sun, bombards Mercury with particular intensity. The Sun's gravitational field shapes Mercury's orbit and even affects its rotation. Solar radiation determines surface temperatures and drives the processes that maintain Mercury's thin exosphere. This close solar relationship also means that Mercury has been difficult to study from Earth. The planet never appears far from the Sun in our sky, which means we can only observe it during twilight hours when the Sun is just below the horizon. At these times, we must look through a thick layer of Earth's atmosphere near the horizon, which blurs and distorts our view. The glare of twilight further complicates observations. For these reasons, Mercury remained one of the least understood planets until the space age brought us the capability to send robotic explorers to study it directly. Mercury's position in the solar system also gives it the shortest year of any planet. A Mercury year, the time required for one complete orbit around the Sun, lasts only about 88 Earth days. This rapid orbital motion is a direct consequence of proximity to the Sun, following the principles established by Kepler's laws of planetary motion. Objects closer to the Sun must move faster to maintain their orbits, balanced against a stronger gravitational pull at shorter distances. The inner solar system, where Mercury resides, is a dynamic region that has evolved significantly over the age of the solar system. During the period known as the Late Heavy Bombardment, approximately 4 billion years ago, the inner planets experienced an intense period of asteroid and comet impacts that shaped their surfaces dramatically. Mercury bears the scars of this violent era, its surface heavily cratered from ancient collisions. The processes that have erased many ancient craters on Earth and resurfaced Venus operate far less efficiently on Mercury, leaving much of this ancient record preserved. Understanding Mercury helps us understand the formation and evolution of terrestrial planets in general. As the most extreme member of this category, orbiting closest to the Sun and possessing the most unusual composition, Mercury provides boundary conditions for theories of planetary formation. Any comprehensive model must explain not only Earth and Venus and Mars, but also this small, dense, swift-moving world that races around our star in a tight orbit. The future habitability of the inner solar system may also depend on understanding worlds like Mercury. As humanity considers expanding beyond Earth, characterizing the environments and resources of other bodies becomes increasingly important. Mercury's permanently shadowed craters contain water ice, a potentially valuable resource for future exploration. Its metallic composition represents a concentration of materials that could theoretically be exploited. While human presence on Mercury remains far in the future, understanding this world contributes to our broader knowledge of solar system environments. As you continue to rest and listen, picture Mercury in your mind as a small, dense world hugging close to our enormous Sun. Imagine the solar furnace blazing overhead, 3 times larger than what we see from Earth. Feel the intense radiation pouring down onto ancient, cratered terrain. This is Mercury's reality, shaped by 4.5 billion years of existence in the most extreme environment the inner solar system offers, the extraordinary orbit of Mercury. Mercury's journey around the Sun is one of the most remarkable in our solar system, characterized by orbital properties that set this world apart from all others. The mathematics of Mercury's motion have challenged and enlightened astronomers for centuries, even playing a crucial role in validating Einstein's theory of general relativity. Let us explore the fascinating orbital dynamics of this swift inner world. Mercury follows an elliptical path around the Sun, as do all planets, but its orbit is considerably more elongated than most of its planetary siblings. Astronomers describe this elongation using a parameter called eccentricity, which ranges from 0 for a perfect circle to values approaching 1 for highly stretched ellipses. Mercury's orbital eccentricity is approximately 0.206, the highest of any planet in our solar system. By comparison, Earth's orbital eccentricity is only about 0.07, making our path around the Sun nearly circular. This high eccentricity means that Mercury's distance from the Sun varies significantly throughout its year. At perihelion, the point of closest approach, Mercury comes within approximately 46 million kilometers of the Sun. At aphelion, the most distant point, this separation increases to approximately 70 million kilometers. The difference between these extremes amounts to about 24 million kilometers, or roughly 16% of Earth's average distance from the Sun. This variation has profound effects on the conditions Mercury experiences throughout its orbit. The intensity of sunlight Mercury receives varies dramatically as a result of this orbital eccentricity. Solar radiation follows an inverse square law, meaning that doubling the distance from the Sun reduces the radiation intensity to 1/4 of its previous value. Because Mercury's distance from the Sun varies by roughly 50% between perihelion and aphelion, the solar flux at these 2 points differs by more than a factor of 2. This creates significant variations in surface heating throughout Mercury's year. Mercury completes one orbit around the Sun in approximately 88 Earth days, giving it the shortest year of any planet. This rapid orbital motion reflects Mercury's position close to the Sun, where orbital velocities must be high to balance the strong gravitational attraction. Mercury travels through space at an average speed of about 47 kilometers per second, compared to Earth's average orbital velocity of about 30 kilometers per second. At perihelion, when Mercury is closest to the Sun and moving fastest, its velocity exceeds 58 kilometers per second. The combination of Mercury's orbital period and its rotation period creates one of the most unusual day-night cycles in the solar system. For many years, astronomers believed that Mercury was tidally locked to the Sun, rotating once per orbit so that one face perpetually faced the solar furnace, while the other remained in eternal darkness. This misconception, established by Giovanni Schiaparelli in the 1880s, persisted until 1965, when radar observations from Earth revealed the truth. Mercury actually rotates on its axis once every 59 Earth days, which is not the same as its 88-day orbital period. However, these two periods are related by a precise mathematical ratio. Mercury rotates exactly 3 times for every 2 orbits around the Sun. This 3-to-2 spin-orbit resonance creates a remarkable situation in which a solar day on Mercury, the time from one noon to the next, lasts 2 Mercury years, or approximately 176 Earth days. Understanding this spin-orbit resonance requires careful thought. As Mercury orbits the Sun, it also rotates on its axis, but not fast enough to keep pace with its changing orbital position. The result is that the Sun appears to move slowly across Mercury's sky, rising in the east and setting in the west, but taking an extraordinarily long time to complete its journey. Someone standing on Mercury's surface would experience roughly 88 Earth days of sunlight followed by 88 Earth days of darkness. The resonance between Mercury's rotation and orbit is not coincidental, but results from gravitational interactions over billions of years. Tidal forces from the Sun, caused by the difference in gravitational pull across Mercury's diameter, have gradually influenced the planet's rotation. These forces tend to slow a planet's rotation and can eventually lock it into a resonance with its orbit. Mercury's high orbital eccentricity prevents simple synchronous rotation, where one face always points toward the Sun, and instead has settled into this 3-to-2 resonance as the most stable configuration. Mercury's orbit presents another extraordinary feature that helped revolutionize physics in the early 20th century. The point of Mercury's closest approach to the Sun its perihelion, does not remain fixed in space but instead slowly rotates around the Sun over time. This phenomenon is called perihelion precession, and it occurs for all planets to varying degrees due to the gravitational influence of other planets in the solar system. Astronomers in the 19th century measured Mercury's perihelion precession carefully and found that it exceeded what Newtonian gravity could explain. After accounting for the gravitational pulls of Venus, Earth, Jupiter, and all other known bodies, there remained an unexplained advance of Mercury's perihelion of about 43 arcseconds per century. This tiny discrepancy troubled astronomers for decades. Some proposed the existence of an undiscovered planet closer to the Sun than Mercury, which they named Vulcan, whose gravity might explain the extra precession. The mystery was resolved by Albert Einstein in 1915 when he completed his general theory of relativity. This new theory of gravity, which describes gravitational effects as arising from the curvature of spacetime caused by mass, predicted exactly the additional 43 arcseconds per century of perihelion precession that astronomers had observed. Mercury's proximity to the Sun, where spacetime curvature is strongest in our solar system, makes it the planet most sensitive to these relativistic effects. The successful explanation of Mercury's perihelion precession provided one of the first confirmations of general relativity and remains a cornerstone validation of Einstein's theory. Mercury thus holds a special place in the history of physics, serving as a natural laboratory for testing our most fundamental understanding of gravity. Every time Mercury completes an orbit, its perihelion has shifted slightly, a tiny but measurable signature of the curvature of spacetime near our Sun. Mercury's orbital inclination, the tilt of its orbital plane relative to Earth's orbital plane, is also notably high at about 7 degrees. This means that Mercury spends most of its time either above or below the plane in which Earth orbits, and transits of Mercury across the Sun's disk occur relatively infrequently. These transits, which require Mercury to cross the plane of Earth's orbit while positioned between Earth and the Sun, happen only about 13 times per century. The orbital dynamics of Mercury also produce interesting visual phenomena as seen from Earth. Because Mercury orbits inside Earth's orbit, it displays phases like the Moon and Venus, waxing and waning as different portions of its sunlit side face us. At inferior conjunction, when Mercury passes between Earth and the Sun, we see its dark night side, and the planet is invisible except during rare transits. At superior conjunction, when Mercury is on the far side of the Sun from Earth, we see its fully illuminated day side, but it appears very small due to its distance. The points of greatest elongation, when Mercury appears farthest from the Sun in our sky, provide the best opportunities for observation from Earth. These elongations occur when Mercury lies roughly along a line from Earth tangent to its orbit around the Sun. At greatest eastern elongation, Mercury appears in the evening sky after sunset. At greatest western elongation, it appears in the morning sky before sunrise. Even at these optimal times, Mercury never strays more than about 28 degrees from the Sun's position, requiring observers to look near the horizon during twilight. These orbital characteristics have shaped how humans have perceived Mercury throughout history. The planet's swift motion, its tendency to appear alternately in morning and evening skies, and its inability to venture far from the solar glare, all influence the mythological associations ancient cultures developed. The messenger god, swift and elusive, perfectly captured the observational qualities of this innermost planet. As you rest and let these orbital concepts wash over you, imagine Mercury tracing its elongated path around the Sun. Picture the planet speeding up as it approaches perihelion, slowing as it swings out toward aphelion, endlessly repeating this celestial dance. 3 rotations for every 2 orbits, 176 Earth days from noon to noon, and a slow precession of the orbit itself that speaks to the deep structure of space-time. Mercury's motion embodies mathematics made visible, orbital mechanics written across the inner solar system, physical characteristics and composition. Having explored Mercury's orbit, let us now turn our attention inward, examining the physical nature of this small but remarkable world. Mercury's composition and structure reveal a planet unlike any other in our solar system, a dense metallic body wrapped in a thin rocky shell. Understanding what Mercury is made of and how it is structured helps us comprehend both its history and its place among the family of planets. Mercury is a diminutive world when measured by size. Its diameter spans approximately 4,885 kilometers, making it the smallest planet in our solar system since Pluto's reclassification as a dwarf planet. For comparison, Earth's diameter measures approximately 12,742 kilometers, more than 2.5 times larger. Mercury is only slightly larger than Earth's moon, which has a diameter of about 3,475 kilometers. Despite its small size, Mercury carries considerable mass concentrated into its compact frame. The planet weighs in at approximately 330 billion trillion kilograms, or about 5.5% of Earth's mass. When we combine this mass with Mercury's small volume, we arrive at a remarkable average density of approximately 5,427 kilograms per cubic meter. This makes Mercury the second densest planet in our solar system, exceeded only by Earth at approximately 5,515 kilograms per cubic meter. However, Earth's higher density is largely due to gravitational compression. The immense pressure within Earth's interior squeezes material to higher densities than it would otherwise possess. Mercury, being much smaller, experiences far less internal compression. When scientists calculate what is called uncompressed density, accounting for this gravitational effect, Mercury actually emerges as the densest planet of all. This exceptional density points to an unusual composition, specifically an extraordinary abundance of iron. The dominant feature of Mercury's interior is its enormous core, believed to consist primarily of iron, with some nickel and possibly sulfur or other lighter elements mixed in. This core extends approximately 2,000 kilometers from Mercury's center, accounting for roughly 85% of the planet's radius. If we could remove Mercury's outer layers and expose the core, we would find a metallic sphere comparable in size to our moon. Surrounding the core lies a mantle composed of silicate minerals, similar in general composition to Earth's mantle, but much thinner in proportion to the planet's size. This mantle extends from the top of the core to within about 50 kilometers of the surface. The exact thickness and composition of Mercury's mantle remain subjects of ongoing research, with data from spacecraft missions continuing to refine our understanding. The outermost layer of Mercury is its crust, a shell of relatively low-density, rocky material, perhaps 30 to 50 kilometers thick on average. The crust displays considerable variation across Mercury's surface, with some regions showing evidence of volcanic flooding and others preserving the most ancient, heavily cratered terrain. The materials composing Mercury's crust include various silicate minerals, with compositions that suggest complex geological history. The question of why Mercury possesses such an enormous core relative to its overall size has intrigued planetary scientists for decades. Several hypotheses have been proposed, each with supporting evidence and remaining questions. Understanding Mercury's unusual composition provides insights into the conditions and processes that operated in the early solar system. One hypothesis suggests that Mercury formed in a region of the protoplanetary disk naturally enriched in metallic materials. Close to the young Sun, temperatures would have been high enough to vaporize many silicate minerals and lighter compounds, potentially leaving behind material with a higher proportion of refractory metals. This temperature-dependent sorting could have provided Mercury with more iron-rich building blocks than planets forming farther from the Sun received. A second hypothesis proposes that Mercury once had a much larger silicate mantle that was stripped away by one or more giant impacts early in solar system history. Such collisions could have blasted much of Mercury's original rocky material into space, leaving behind the dense core surrounded by only a remnant mantle. Computer simulations have shown that such impacts could produce a planet with Mercury's current composition, though the specific impact scenarios remain debated. A third hypothesis involves solar radiation during Mercury's formation. Intense radiation from the young Sun might have eroded silicate materials from the forming planet through a process called photoevaporation, preferentially removing lighter elements and leaving behind the denser metallic components. This mechanism could work in conjunction with other processes to explain Mercury's composition. Recent data from the Messenger spacecraft and ongoing analysis have added complexity to these hypotheses. Mercury's surface composition shows higher abundances of volatile elements like sulfur and potassium than some impact scenarios would predict. These elements should have been largely stripped away or vaporized if Mercury experienced the violent history some models suggest. Reconciling these observations with formation theories remains an active area of research. The surface gravity on Mercury is approximately 3.7 meters per second squared, or about 38% of Earth's surface gravity. A person who weighs 100 pounds on Earth would weigh only 38 pounds standing on Mercury. This relatively weak gravity, comparable to that of Mars, means that Mercury could not retain a substantial atmosphere, even if its high temperatures did not ensure the rapid escape of atmospheric gases. Mercury possesses no natural satellites or moons. This makes Mercury one of only 2 planets in our solar system without moons, sharing this distinction with Venus. The absence of moons could be related to Mercury's formation history, its proximity to the Sun, or simply the chance outcomes of early solar system dynamics. The gravitational influence of the nearby Sun makes maintaining stable satellite orbits around Mercury more challenging than around more distant planets. The shape of Mercury is very nearly spherical, deviating from a perfect sphere by only a tiny amount. The planet's rapid rotation during earlier epochs may have produced a slightly oblate shape, flattened at the poles and bulging at the equator, but Mercury's current slow rotation has allowed it to relax towards sphericity. Any remaining deviation from spherical is too small to detect without precise measurements. Mercury's axis of rotation is almost perfectly perpendicular to its orbital plane, tilted by less than 1 degree. This minimal axial tilt means that Mercury experiences essentially no seasons in the sense that Earth does. On Earth, the 23-degree axial tilt causes different hemispheres to receive more direct sunlight at different times of year, producing our familiar cycle of seasons. Mercury's near-zero tilt eliminates this effect, with both hemispheres receiving essentially equal solar exposure year-round. This minimal axial tilt has an important consequence for Mercury's polar regions. The floors of some craters near Mercury's poles never receive direct sunlight, remaining in permanent shadow cast by crater rims that rise above the local horizon. These permanently shadowed regions experience some of the coldest temperatures in the inner solar system, despite Mercury's overall proximity to the Sun. As we will explore later, these frigid crater floors harbour water ice, a remarkable discovery on this seemingly hellish world. The physical characteristics of Mercury combine to create a unique planetary environment, a small dense world, hugging close to the Sun, with an enormous iron core, minimal atmosphere, extreme temperature variations, and no moons to accompany it on its swift orbit. These attributes make Mercury a fascinating subject for planetary science, offering insights into processes and conditions that differ dramatically from Earth's familiar environment. As your mind drifts and relaxes, hold the image of Mercury's internal structure in your imagination. Picture the vast iron core, larger in proportion than any other planet's, surrounded by its thin rocky mantle and crust. This dense little world has survived 4.5 billion years in the harsh environment of the inner solar system, preserving records of ancient processes and continuing to challenge our understanding of planetary formation and evolution. The cratered landscape and surface features. Mercury's surface tells a story written in stone, a chronicle of cosmic violence and geological processes preserved across billions of years. Unlike Earth, where erosion, plate tectonics, and volcanic activity constantly resurface our planet and erase ancient features, Mercury has changed relatively little since the heavy bombardment that scarred it early in solar system history. Let us explore this ancient, battered landscape in detail, discovering the features that make Mercury's surface unique among worlds. The most striking characteristic of Mercury's surface is its extensive cratering. Impact craters of all sizes pepper the planet's terrain, from tiny pits measuring meters across to vast impact basins hundreds of kilometers in diameter. These craters record a history of collisions with asteroids, comets, and other debris that has accumulated over more than 4 billion years. The sheer density of craters on some portions of Mercury's surface rivals that of the Moon's heavily cratered highlands. The process of crater formation begins when a solid object strikes Mercury's surface at high velocity. Objects in the inner solar system typically travel at tens of kilometers per second, carrying tremendous kinetic energy. When such an object collides with Mercury, it releases this energy explosively, vaporizing both the impactor and a portion of the target's surface, excavating a bowl-shaped cavity, and throwing debris outward to form an ejector blanket surrounding the crater. Larger impacts can trigger additional processes, including central peak formation, where the crater floor rebounds upward, and multiple ring structures in the very largest basins. Mercury's craters range across a vast spectrum of sizes. The largest confirmed impact structure is the Caloris Basin, one of the most impressive features in the entire solar system. This enormous basin measures approximately 1,550 kilometers in diameter, large enough that the entire state of Texas could fit inside it with room to spare. The impact that created Caloris was so powerful that it sent shockwaves propagating through Mercury's interior, producing a region of jumbled hilly terrain on the exact opposite side of the planet, directly antipodal to the impact site. The Caloris Basin formed approximately 3.9 billion years ago during the period of late heavy bombardment that affected all the inner planets. Its floor has been partially covered by subsequent volcanic flows, which have smoothed some of the original impact features. The basin's rim rises in a ring of mountains and cliffs, with concentric fractures and ridges extending outward into the surrounding terrain. Within the basin lies a region of strange radiating troughs that scientists have named the Pantheon Fossae, a pattern that remains not fully explained. Beyond Caloris, numerous other large impact basins mark Mercury's surface. The Rembrandt Basin, discovered by the Messenger spacecraft, spans approximately 715 kilometers and is one of the best preserved large basins on Mercury. The Beethoven Basin measures approximately 630 kilometers in diameter. The Tolstoy Basin, the Dostoevsky Basin, and dozens of other named impact structures record the violent history of the inner solar system. Smaller craters are even more numerous, covering nearly every portion of Mercury's surface. These features display the characteristic morphologies of impact craters: raised rims, bowl-shaped interiors, and surrounding ejecta blankets. Fresher craters appear more sharply defined, with bright ray systems extending outward from the impact site where material ejected during crater formation struck the surrounding terrain. Older craters have been softened by subsequent smaller impacts. Their rays faded and their rims degraded. The naming of craters on Mercury follows an international convention established by the International Astronomical Union. Impact craters on Mercury are named after artists, musicians, painters, and authors who have made outstanding or fundamental contributions to their field and have been dead for more than 3 years. This naming scheme has populated Mercury's surface with a remarkable collection of cultural references. Walking across a map of Mercury, one encounters craters named for Beethoven, Tolstoy, Shakespeare, Michelangelo, Rembrandt, Bach, Chopin, Dickens, Twain, and countless other creative figures from human history. Not all of Mercury's surface is ancient, cratered highlands. Significant portions of the planet are covered by smooth plains that represent volcanic flooding events from Mercury's past. These plains fill low-lying regions, particularly crater floors, and the interiors of impact basins, where lavas erupted onto the surface and spread across the terrain. The smooth plains are less heavily cratered than the older highlands, indicating they formed more recently and covered older surfaces. The volcanic activity that created these smooth plains occurred primarily between 4.1 and 3.5 billion years ago, during a period when Mercury's interior was hotter and more active than today. Heat from the decay of radioactive elements and residual heat from the planet's formation drove melting in Mercury's mantle, producing magmas that rose to the surface through fractures and vents. The resulting volcanic floods resemble the lunar Maria, the dark, smooth regions visible on the Moon's face, though Mercury's plains are somewhat different in composition. One of Mercury's most distinctive surface features is its network of lobate scarps, curving cliffs that snake across the terrain for hundreds of kilometers. These scarps are actually the surface expressions of thrust faults, fractures along which portions of Mercury's crust have been pushed over adjacent terrain. Lobate scarps range from tens of kilometers to over 500 kilometers in length, with heights of hundreds of meters to several kilometers. The prevalence of lobate scarps tells us something fundamental about Mercury's history. The planet has been shrinking. As Mercury's core cooled and solidified over billions of years, it contracted, and the surface crust cracked and buckled to accommodate this reduction in volume. Scientists estimate that Mercury's radius has decreased by approximately 7 kilometers since its formation, a significant amount for such a small world. The lobate scarps are the scars of this global contraction, preserved in Mercury's rocky surface. Mercury also displays features called wrinkle ridges, low winding ridges that typically occur within smooth plain regions. These ridges formed as the plane's material compressed, possibly due to the overall global contraction or to the subsidence and flexing of impact basin floors. Wrinkle ridges are common on the lunar Maria as well, indicating similar geological processes at work on both worlds. More puzzling are the hollows, strange irregularly shaped depressions that appear bright and often have blue-tinged halos in enhanced colour images. Hollows tend to occur on crater floors, central peaks, and walls, and they appear remarkably fresh with sharp edges and no superimposed impact craters. Their pristine appearance suggests they may still be actively forming today, though the process responsible remains under investigation. One hypothesis suggests that volatile substances within Mercury's crust are sublimating, turning directly from solid to gas and escaping to space, leaving behind these peculiar depressions. The surface composition of Mercury has been revealed through spectroscopic measurements from orbit and provides additional constraints on the planet's geological history. Mercury's surface is relatively dark, reflecting only about 6% of the sunlight that strikes it, similar to our Moon's reflectivity. The surface is rich in silicate minerals, but shows some compositional differences from the Moon and other rocky bodies. Higher abundances of sulfur and lower abundances of iron in surface materials compared to the lunar surface suggest different formation conditions or subsequent modification processes. Color variations across Mercury's surface, though subtle, reveal compositional differences. When spacecraft images are processed to enhance color contrasts, Mercury displays a range of tones from dark blue to bright orange. These variations relate to differences in mineral composition and geological history. Younger volcanic deposits, fresher crater ejecta, and regions of different crustal composition all contribute to Mercury's subtle but real color palette. The terrain around the Caloris Basin antipode, called the chaotic terrain or weird terrain, deserves special mention. When the Caloris impactor struck Mercury, seismic waves propagated through the planet's interior and converged on the opposite side of the globe. This focusing of seismic energy disrupted the surface, creating a region of broken, hilly terrain characterized by blocks of crust tilted at various angles. This feature demonstrates the intimate connection between large impacts and global-scale planetary processes. Mercury's surface has also been shaped by processes less dramatic than giant impacts. Small impacts accumulate over time, gradually breaking down surface rocks and generating a layer of fragmented material called regolith. Solar wind bombardment sputters atoms from surface materials. Micrometeorite impacts add to the grinding process. Extreme temperature cycles cause rocks to expand and contract, potentially contributing to their breakdown. Together, these processes produce a surface layer of fine debris overlying more coherent bedrock. As you drift deeper into relaxation, visualize Mercury's ancient surface stretching before you. Picture the vast expanse of the Caloris Basin, its mountainous rim rising against the black sky. Imagine standing in a younger crater, its central peak catching sunlight, while the floor remains in shadow. See the long, curving line of a Lobat scarp crossing the terrain, evidence of a planet that has been slowly shrinking for billions of years. This is the face of Mercury, a record of cosmic history written in rock and crater. Temperature extremes and the exosphere. Mercury experiences temperature variations more extreme than any other planet in our solar system, swinging between scorching heat and bitter cold over the course of its long day. This world possesses virtually no atmosphere to moderate these extremes, leaving its surface directly exposed to the harsh environment of the inner solar system. Let us explore the thermal conditions on Mercury and the tenuous envelope of gas that barely constitutes an atmosphere. The day side of Mercury is among the hottest places in the inner solar system. Surface temperatures during the day can reach approximately 430 degrees Celsius, hot enough to melt lead, zinc, and many other metals. At perihelion, when Mercury passes closest to the Sun and receives maximum solar radiation, temperatures climb even higher. The combination of proximity to the Sun and the length of the solar day, which allows the surface to heat continuously for many Earth weeks, drives these extreme daytime temperatures. Yet Mercury is not the hottest planet in our solar system. That distinction belongs to Venus, whose dense carbon dioxide atmosphere creates a runaway greenhouse effect that elevates surface temperatures to approximately 465 degrees Celsius. Higher than Mercury, despite Venus being nearly twice as far from the Sun. Mercury lacks this atmospheric blanket, which prevents it from retaining heat as efficiently as Venus does. The night side of Mercury experiences the opposite extreme. Without a substantial atmosphere to retain heat, the surface radiates thermal energy directly into the cold of space. Nighttime temperatures plummet to approximately negative 180 degrees Celsius, more than 600 degrees colder than the daytime maximum. This temperature swing of over 600 degrees between day and night exceeds that of any other planet. The length of Mercury's solar day contributes significantly to these extreme temperatures. Because the solar day lasts approximately 176 Earth days, any given point on Mercury's surface experiences roughly 88 Earth days of continuous sunlight, followed by 88 Earth days of continuous darkness. During the long day, the surface has ample time to heat up, reaching equilibrium with the intense solar radiation. During the equally long night, the surface has ample time to cool, approaching equilibrium with the cold of space. Mercury's orbital eccentricity adds another layer of complexity to its thermal environment. The planet receives roughly twice as much solar radiation at perihelion compared to aphelion. This means that noon on Mercury is significantly hotter when the planet is at perihelion than when it is at aphelion. Due to the peculiarities of Mercury's spin-orbit resonance, certain longitudes experience perihelion noon, while others experience aphelion noon. The longitudes that receive peak solar heating when Mercury is closest to the Sun are called hot poles, while those that face the Sun when Mercury is at aphelion are called warm poles. The hot poles of Mercury experience the most extreme heating anywhere on the planet. At these locations, noon occurs when Mercury is closest to the Sun, and the solar heating is most intense. Temperatures at the hot poles during perihelion noon may briefly exceed 450 degrees Celsius. The warm poles, while still experiencing extreme temperatures by earthly standards, remain somewhat cooler because they face the Sun when Mercury is at the farthest point of its orbit. In stark contrast to these scorching regions, Mercury's polar craters harbour some of the coldest temperatures in the inner solar system. The floors of certain craters near the north and south poles are permanently shadowed, never receiving direct sunlight because of Mercury's minimal axial tilt. With no sunlight to warm them and no atmosphere to conduct heat from surrounding regions, these crater floors maintain temperatures below negative 170 degrees Celsius year-round. Some of the coldest spots may be as cold as negative 200 degrees Celsius. These permanently shadowed craters contain water ice, a discovery that surprised many scientists when it was first confirmed. The idea that the closest planet to the Sun could harbour ice seems counterintuitive, but the physics of heat transfer on an airless world permits such apparent paradoxes. Without an atmosphere to carry heat from warm regions to cold ones, adjacent areas on Mercury can maintain dramatically different temperatures indefinitely. The water ice in Mercury's polar craters most likely arrived via comet and asteroid impacts over billions of years. Some of this water migrated across Mercury's surface through various processes until it reached the permanent shadows near the poles, where it became trapped in the extreme cold. Radar observations from Earth first detected the presence of bright, reflective deposits in Mercury's polar craters, and subsequent spacecraft measurements confirmed these deposits as water ice. Mercury possesses what is technically classified as an exosphere rather than a true atmosphere. The distinction relates to density. In a proper atmosphere, gas molecules collide with each other frequently, behaving as a collective fluid. In an exosphere, the density is so low that individual atoms travel on ballistic trajectories without colliding, essentially behaving as independent particles. Mercury's exosphere is extraordinarily tenuous, with a total mass estimated at less than 1,000 kilograms, billions of times less massive than Earth's atmosphere. The composition of Mercury's exosphere includes atoms of hydrogen, helium, oxygen, sodium, potassium, calcium, and magnesium, among other elements. These atoms originate from several sources. Solar wind protons become hydrogen atoms when they strike the surface. Helium atoms from the solar wind and from radioactive decay within Mercury drift through the exosphere. Heavier atoms like sodium and potassium are sputtered from surface minerals by solar wind bombardment and micrometeorite impacts. The sodium component of Mercury's exosphere is particularly interesting and observable. Sodium atoms in the exosphere glow brightly when illuminated by sunlight, emitting characteristic yellow light that astronomers can detect from Earth using specialized instruments. Observations of Mercury's sodium exosphere reveal a dynamic, variable envelope that changes in response to solar activity and surface conditions. At times, the sodium appears concentrated in certain regions. At other times, it streams away from Mercury in a tail pointing away from the Sun. Mercury's exosphere continuously leaks away into space, requiring constant replenishment from surface sources. The tenuous envelope we observe today represents a balance between processes that add atoms to the exosphere and processes that remove them. Solar radiation pressure pushes some atoms away from Mercury entirely. Other atoms follow escape trajectories after gaining sufficient velocity from solar heating. The exosphere is not a static feature but a dynamic system in perpetual flux. The solar wind interacts directly with Mercury's surface because of the minimal atmosphere. Charged particles streaming outward from the Sun strike the surface with little hindrance, implanting themselves in surface materials and sputtering atoms into the exosphere. This solar wind bombardment gradually alters the composition and properties of Mercury's surface materials, a process called space weathering that affects all airless bodies in the solar system. The lack of substantial atmosphere means that Mercury cannot support the kinds of weather phenomena familiar on Earth. There are no clouds, no rain, no wind in the conventional sense. The exosphere is far too thin to transmit sound, so Mercury is a world of absolute silence, except for the vibrations transmitted through the ground from impacts and thermal expansion. The sky from Mercury's surface appears black even during the day because there is no atmosphere to scatter sunlight and create the blue sky we enjoy on Earth. Understanding Mercury's thermal environment and exosphere helps us appreciate the harsh conditions that spacecraft must endure when exploring this world. The extreme temperature swings, intense solar radiation, and bombardment by solar wind particles all pose challenges for mission design. Instruments must function across huge temperature ranges. Spacecraft must be protected from solar heating. Power systems must cope with the nearby solar furnace. The successful missions to Mercury represent impressive engineering achievements. As you rest in comfort, far from Mercury's hostile environment, imagine the contrasts that exist on that small world. Picture the blinding sunlight on the day side, where rocks glow red with heat and the sun looms enormous in the black sky. Then shift to the night side, where the same rocks have cooled to temperatures colder than Antarctica's darkest winter. And somewhere between, at the poles, shadowed crater floors harbour ice that has waited in darkness for billions of years. This is Mercury's thermal reality, a world of extremes unmatched in our solar system. The magnetic field and internal structure. One of the most surprising discoveries about Mercury was the detection of a global magnetic field, a finding that forced scientists to reconsider their understanding of this small world's interior. Magnetic fields arise from specific physical processes, and Mercury's field tells us that this ancient planet remains geologically active in ways that were not initially expected. Let us explore the mysteries of Mercury's magnetism and what it reveals about the planet's deep interior. When the Mariner 10 spacecraft flew past Mercury in 1974, its magnetometer detected a weak but definite magnetic field emanating from the planet. This discovery surprised researchers because Mercury seemed too small and presumably too cold to maintain the kind of active, liquid interior typically required to generate a planetary magnetic field. Mars, which is larger than Mercury, possesses only crustal magnetic anomalies rather than a global field. The Moon has no present-day magnetic field at all. Why should little Mercury be different? Mercury's magnetic field is approximately 1% as strong as Earth's field at the surface, which makes it much weaker than our planet's magnetic shield, but still strong enough to interact significantly with the solar wind. The field is roughly dipolar, meaning it has north and south magnetic poles similar to a bar magnet, though the detailed structure shows some asymmetries. The magnetic axis is tilted only about 5 degrees from Mercury's rotation axis and is offset northward from the planet's centre by a significant fraction of its radius. This northward offset of the magnetic field is one of Mercury's puzzling characteristics. The displacement means that the magnetic field is stronger at the North Pole than at the South Pole, creating an asymmetry in how the field interacts with the solar wind and protects the surface. The southern hemisphere receives more direct solar wind bombardment as a result of this asymmetry, which may have consequences for surface weathering and exosphere generation processes. Planetary magnetic fields like Earth's and presumably Mercury's are generated by a process called the dynamo effect. This process requires 3 ingredients: an electrically conducting fluid, convection or motion of that fluid, and the planet's rotation. When these conditions are met, the motion of the conducting fluid through existing magnetic fields generates electric currents, which in turn create magnetic fields that reinforce and sustain the original field. It becomes a self-sustaining process as long as the necessary conditions persist. For Mercury to have a dynamo-generated magnetic field, it must possess a liquid layer of electrically conducting material in its interior. Given Mercury's iron-rich composition, this conducting layer is almost certainly the outer portion of its iron core. This means that Mercury's core cannot be entirely solid, but must contain a substantial liquid component even after 4.5 billion years of cooling. The persistence of liquid iron in Mercury's core requires explanation. Small planetary bodies tend to cool more rapidly than large ones, and Mercury has had plenty of time to solidify completely. Several mechanisms have been proposed to explain why Mercury's core remains partially liquid. One possibility involves the presence of lighter elements, like sulfur, mixed into the core. Adding sulfur to iron lowers the melting point of the mixture, allowing it to remain liquid at lower temperatures than pure iron would permit. Data from the MESSENGER mission support the presence of a relatively light element-rich core composition. Measurements of Mercury's gravity field and its libration, or slight wobble as it rotates, indicate that the outer core remains liquid and that the core as a whole is larger than previously estimated. These findings are consistent with a core containing significant amounts of sulfur or other light elements that have kept the outer portions molten despite billions of years of cooling. The structure of Mercury's interior, as currently understood, consists of several distinct layers. At the centre lies a solid inner core composed primarily of iron that has solidified as the planet cooled. Surrounding this solid inner core is a liquid outer core, also dominated by iron, but remaining molten due to its composition and thermal state. This liquid layer is where the magnetic field dynamo operates. Outside the core lies the silicate mantle, and at the surface, the crust. The large size of Mercury's core relative to the planet as a whole means that the liquid outer core occupies a substantial fraction of Mercury's interior. This extensive liquid layer provides ample volume for dynamo processes to operate, generating the observed magnetic field. The specific geometry and dynamics of convection within the liquid core determine the detailed properties of the magnetic field, including its strength, structure, and the offset that observations have revealed. Mercury's magnetic field creates a magnetosphere, a region of space dominated by the planet's magnetic field rather than the solar wind's magnetic field. Mercury's magnetosphere is much smaller than Earth's in absolute terms, and even smaller relative to the planet's size. This compact magnetosphere is compressed by the intense solar wind at Mercury's orbital distance, where the flow of solar particles is much denser than at Earth. The interaction between Mercury's magnetosphere and the solar wind is dynamic and complex. The solar wind flows around the magnetosphere, creating a bow shock upstream, where the supersonic solar wind is suddenly slowed and heated. The magnetosphere has a tail stretching in the anti-sunward direction, formed by magnetic field lines dragged away from Mercury by the solar wind flow. Within the magnetosphere, charged particles from the solar wind can become trapped, though Mercury's small magnetosphere provides less protection than Earth's more extensive magnetic shield. Magnetic reconnection, a process in which magnetic field lines from different sources break and reconnect in new configurations, plays an important role in Mercury's magnetospheric dynamics. When the interplanetary magnetic field carried by the solar wind has a favourable orientation, reconnection occurs on the dayside magnetosphere, allowing solar wind particles to enter. Subsequent reconnection in the magnetotail returns these particles to the solar wind or accelerates them toward Mercury's surface. The solar wind particles that reach Mercury's surface contribute to space weathering processes and can stimulate the release of atoms into the exosphere. The asymmetry of Mercury's magnetic field, with its weaker protection over the southern hemisphere, may result in enhanced surface effects in that region. Understanding these interactions provides insights into how airless bodies throughout the solar system respond to the solar wind. Studying Mercury's magnetic field also provides insights into conditions in the early solar system and the processes of planetary differentiation. Mercury formed and evolved differently from the other terrestrial planets, and its magnetic field is one expression of that distinct history. The survival of a dynamo in such a small old planet constrains theories of planetary thermal evolution and core composition. The Messenger mission greatly expanded our understanding of Mercury's magnetic field through years of orbital measurements. The spacecraft's magnetometer mapped the field in 3 dimensions, revealing its structure and variability. Extended orbital operations allowed observations during different phases of solar activity, documenting how the magnetosphere responds to changing solar wind conditions. Future missions, particularly BepiColombo, currently en route to Mercury, will continue to study the magnetic field and magnetosphere. With improved instruments and longer observation periods, scientists expect to further refine our understanding of Mercury's interior structure, dynamo processes, and solar wind interactions. Each new measurement adds detail to our picture of this magnetically active little world. As you rest peacefully, consider the hidden activity deep within Mercury. While the surface appears ancient and static, the interior remains dynamic, with molten iron churning in the outer core and generating the magnetic field that reaches out into space. This small world, seemingly so different from our own, shares with Earth the fundamental process of magnetic field generation. Deep beneath the cratered surface, Mercury's heart continues to beat. Mariner 10, humanity's first visit, For centuries, Mercury remained a dot of light glimpsed briefly at twilight, its surface features unknown, and its nature a subject of speculation. All of this changed in the 1970s when humanity sent its first robotic emissary to the solar system's innermost planet. The Mariner 10 mission opened a new chapter in our understanding of Mercury, revealing a world far more complex and interesting than anyone had anticipated. Let us explore this pioneering mission that gave us our first close-up views of Mercury. Mariner 10 was the last spacecraft in NASA's Mariner series, a program that had successfully explored the inner solar system throughout the 1960s. Previous Mariner missions had visited Mars and Venus, returning valuable data and images from these worlds. Mariner 10 was designed to extend this exploration to Mercury, the only classical planet that had not yet been visited by spacecraft. The mission faced significant challenges from the outset. Mercury's proximity to the Sun made it a difficult target to reach. A spacecraft travelling directly from Earth to Mercury would require an enormous amount of fuel to match velocities with the fast-moving inner planet. The mission designers needed a clever solution to make the mission feasible within practical constraints. The answer came in the form of a gravity assist, a technique that uses a planet's gravitational field to alter a spacecraft's trajectory and velocity. Mariner 10 would first fly past Venus, using that planet's gravity to bend its path and reduce its velocity, thereby dropping it into an orbit that would intersect Mercury's position. This maneuver not only made the Mercury mission possible, but also allowed the spacecraft to conduct valuable observations of Venus along the way. Mariner 10 launched on November 3, 1973, from Kennedy Space Center in Florida, carried aloft by an Atlas Centaur rocket. The spacecraft departed Earth and began its journey toward the inner solar system. Approximately 3 months later, on February 5, 1974, Mariner 10 swept past Venus at a distance of about 5,700 kilometers, returning images and data from the cloud-shrouded world, while simultaneously receiving the gravitational boost that would send it on toward Mercury. The Venus flyby was scientifically productive in its own right. Mariner 10's cameras captured images of Venus's upper cloud patterns, revealing atmospheric circulation features that had not been clearly seen before. The ultraviolet images showed a distinctive Y-shaped cloud pattern that rotates around the planet far faster than Venus itself rotates. These observations contributed significantly to our understanding of Venus's atmospheric dynamics. With the Venus gravity assist accomplished, Mariner 10 fell inward toward Mercury on a trajectory carefully designed to bring the spacecraft close to the planet while minimizing relative velocity. On March 29, 1974, Mariner 10 made its first flyby of Mercury, passing within approximately 703 kilometers of the surface. This encounter marked humanity's first close-up look at the innermost planet. The images returned from this first flyby revealed a world bearing a striking resemblance to the Moon. In some respects, yet clearly different in others. Mercury's surface was heavily cratered, as expected for an airless body with ancient terrain. But the distribution and characteristics of the craters, along with other surface features, indicated a geological history distinct from the Moon's. Plains regions, scarps, and subtle colorations all provided clues to Mercury's past. Perhaps the most significant discovery from Mariner 10 was the detection of Mercury's magnetic field. The spacecraft's magnetometer recorded the unmistakable signature of a global magnetic field as Mariner 10 passed through the region of space dominated by Mercury's influence. This discovery was entirely unexpected. Conventional wisdom held that small planets like Mercury should have cooled too thoroughly to maintain the liquid core necessary for magnetic field generation. Mercury's field forced scientists to reconsider their models of planetary interiors. Mariner 10's orbit around the Sun after the first Mercury encounter was designed to bring the spacecraft back to Mercury for additional flybys. Due to a fortunate alignment between Mariner 10's orbital period and Mercury's year, the spacecraft returned to Mercury approximately once every 2 Mercury years, or once per Mariner orbit. This resonance allowed multiple encounters with a single spacecraft. The second Mercury flyby occurred on September 21, 1974, when Mariner 10 passed within approximately 48,000 kilometers of the surface. This more distant flyby provided additional mapping coverage and allowed measurements at different positions relative to Mercury's magnetosphere. The third and final flyby took place on March 16, 1975, with the spacecraft passing within approximately 327 kilometers of the surface, the closest approach of the mission. The 3 flybys together imaged approximately 45% of Mercury's surface. The remaining 55% remained unseen, hidden on the night side during each flyby. Due to the resonance between Mariner 10's orbit and Mercury's, each flyby viewed nearly the same hemisphere of the planet. Complete mapping of Mercury would have to wait for a later mission with a different orbital geometry. Among the features revealed by Mariner 10 was the Caloris Basin, one of the largest impact structures in the solar system. The spacecraft imaged roughly half of this enormous basin, with the terminator, the line between day and night, cutting across its center during the first flyby. The full extent and nature of Caloris would not be revealed until decades later when another spacecraft visited Mercury. Mariner 10 also observed the lobate scarps that snake across Mercury's surface, those features that would later be interpreted as evidence of global planetary shrinkage. The spacecraft's cameras captured smooth plains, regions interpreted as volcanic deposits, crater rays, and the general morphology of the cratered terrain. Each image added to our understanding of Mercury's geological history. The mission faced challenges throughout its operational life. Shortly after launch, one of the spacecraft's 2 cameras failed, reducing imaging capabilities. The attitude control system experienced problems that engineers had to work around through creative use of solar radiation pressure on the spacecraft's solar panels. By the third Mercury flyby, the attitude control gas had been nearly exhausted, limiting the spacecraft's ability to orient itself for optimal observations. Mariner 10's mission officially ended on March 24, 1975, when the attitude control gas was finally depleted and the spacecraft could no longer maintain the orientation needed to keep its antenna pointed toward Earth. The spacecraft presumably continues to orbit the Sun today, though it has been silent for nearly 50 years. Its orbit occasionally brings it close to Mercury, a ghost ship still visiting the world it helped us discover. The legacy of Mariner 10 extended far beyond its operational lifetime. The images and data it returned shaped our understanding of Mercury for more than 3 decades until the next mission arrived. The detection of the magnetic field stimulated research into planetary dynamos and interior structures. The gravity assist technique it pioneered became a standard tool for planetary exploration, enabling missions throughout the solar system. Mariner 10 proved that Mercury was a world worthy of continued attention, a place with geological complexity, unexpected magnetic activity, and a wealth of scientific questions awaiting answers. The spacecraft demonstrated that robotic exploration could reveal secrets that no amount of telescopic observation could uncover. It blazed a trail that later missions would follow, opening Mercury to the space age. As you relax and reflect on this remarkable mission, imagine Mariner 10 speeding through the inner solar system, its instruments turned toward the cratered surface of Mercury. Picture the radio signals traveling from spacecraft to Earth, carrying images of a world that no human eye had ever seen clearly before. This was exploration at its finest, extending human knowledge into unknown regions and finding wonders beyond expectation. Messenger, unlocking Mercury's secrets. More than 30 years after Mariner 10 fell silent, a new spacecraft arrived at Mercury to continue the exploration that Mariner had begun. Messenger, an acronym for Mercury surface, space environment, geochemistry, and ranging, became the first mission to orbit Mercury, conducting a comprehensive study that revolutionized our understanding of this small, dense world. Let us explore the remarkable achievements of this groundbreaking mission. Messenger was conceived as an ambitious undertaking, aiming not just to fly past Mercury, but to enter orbit and study the planet over an extended period. Orbital operations would allow comprehensive global mapping, repeated observations of changing phenomena, and investigations impossible during brief flybys. The mission would answer questions raised by Mariner 10 and explore aspects of Mercury that had not been investigated at all. The challenges of reaching Mercury and entering orbit were formidable. A spacecraft carrying enough fuel to fly directly from Earth to Mercury orbit would be prohibitively massive. Messenger's designers employed an elaborate trajectory involving multiple gravity assists from Earth, Venus, and Mercury itself to gradually reduce the spacecraft's velocity relative to Mercury, making orbital insertion possible with practical fuel loads. Messenger launched on August 3, 2004, from Cape Canaveral Air Force Station in Florida. The spacecraft then embarked on a journey of nearly 7 years' duration before entering Mercury orbit. During this time, Messenger flew past Earth once, past Venus twice, and past Mercury 3 times. Each gravity assist refined the trajectory, bringing the spacecraft closer to the conditions needed for Mercury orbit insertion. The 3 Mercury flybys in 2008 and 2009 provided valuable science opportunities before orbital operations began. These encounters imaged large portions of Mercury's surface that Mariner 10 had not seen, including the side that had remained hidden during all 3 Mariner flybys. For the first time, scientists saw the complete Caloris Basin, revealing its full extent and the patterns of features within it. The flyby observations also detected unusual surface compositions and unexpected geological features. On March 18, 2011, Messenger fired its main engine for approximately 15 minutes, slowing the spacecraft enough for Mercury's gravity to capture it into orbit. This moment represented a historic achievement. Humanity had placed a spacecraft in orbit around the solar system's innermost planet. The primary science mission was set to last 1 Earth year, but successful operations led to extended missions that ultimately kept Messenger functioning until 2015. Messenger's scientific instrument suite was designed to investigate Mercury comprehensively. The spacecraft carried cameras for imaging, spectrometers for determining surface composition, a laser altimeter for mapping topography, a magnetometer for studying the magnetic field, and instruments for measuring the space environment around Mercury. Together, these instruments gathered data that transformed our understanding of Mercury. The imaging system mapped Mercury's entire surface in unprecedented detail. Unlike Mariner 10, which saw only about half the planet, Messenger observed every portion of Mercury's surface. The complete global map revealed features that had never been seen before, including volcanic vents, peculiar depressions called hollows, and impact craters of all sizes. High-resolution images of particular features supplemented the global coverage, revealing details down to meters per pixel in some areas. Messenger's measurements of Mercury's surface composition yielded surprises. The planet's surface contained higher abundances of volatile elements like sulfur, potassium, and sodium than scientists had expected based on some formation scenarios. The ratio of potassium to thorium, an indicator of how much heating the surface material had experienced, suggested that Mercury's surface had not been subjected to the extreme heating some formation models predicted. These compositional findings constrained theories of how Mercury formed and evolved. One of Messenger's most celebrated discoveries was confirmation of water ice at Mercury's poles. Radar observations from Earth had previously detected bright, reflective material in permanently shadowed craters near the poles, and Messenger verified that this material is indeed water ice. The spacecraft's measurements revealed that some of the ice is covered by a dark layer of organic material, insulating it from any warming. The discovery of ice on the closest planet to the Sun captured public imagination and demonstrated that volatiles can survive in unexpected places. The magnetic field measurements from Messenger greatly expanded our knowledge of Mercury's magnetosphere. The spacecraft observed the magnetic field from orbit over an extended period, mapping its three-dimensional structure and documenting its variability. The northward offset of the magnetic field was confirmed and measured precisely. Interactions between the magnetosphere and the solar wind were observed directly, showing how this small magnetosphere responds to the intense particle bombardment at Mercury's orbital distance. Messenger's gravity measurements, combined with observations of Mercury's rotation, provided information about the planet's interior structure. The data indicated that Mercury's outer core remains liquid, consistent with the existence of the magnetic field. The measurements also suggested that the core is larger than previously estimated and likely contains substantial amounts of lighter elements mixed with the iron. These findings helped constrain models of Mercury's internal structure and thermal evolution. The discovery of hollows was entirely unexpected. These peculiar depressions, with their bright interiors and often bluish halos, appear remarkably fresh and may still be forming today. They occur in association with certain types of surface material, suggesting that volatile substances within these materials are escaping to space and leaving behind the hollow depressions. The hollows demonstrated that Mercury is not as geologically static as it might appear, with active processes continuing to modify the surface. Messenger also revealed extensive evidence of past volcanic activity on Mercury. The spacecraft imaged volcanic vents, some surrounded by bright pyroclastic deposits, indicating explosive eruptions. Large smooth plains were confirmed as volcanic in origin, the products of extensive lava flooding billions of years ago. The volcanic history of Mercury proved more complex and long-lasting than some scientists had anticipated. The extended mission phases allowed Messenger to descend to lower orbits, approaching to within about 15 kilometers of Mercury's surface in some cases. These low-altitude passes provided the highest resolution observations of the entire mission, revealing surface details never seen before. The low orbits also permitted more sensitive measurements of the magnetic field and gravity field near the surface. Messenger's mission concluded on April 30th, 2015, when the spacecraft ran out of the propellant needed to maintain its orbit. Without the ability to make orbital corrections, Messenger's orbit decayed until the spacecraft struck Mercury's surface at approximately 3.9 kilometers per second, creating a new impact crater estimated at 16 meters in diameter. This final impact was planned, bringing the spacecraft's journey to a fittingly Mercurian end. The scientific legacy of Messenger continues to unfold as researchers analyze the vast archive of data the mission collected. More than 10 terabytes of science data were returned during the mission, enough to keep scientists occupied for many years. Papers continue to be published, findings continue to be refined, and our understanding of Mercury continues to deepen based on Messenger's observations. Messenger transformed Mercury from one of the least understood planets to one for which we have detailed, comprehensive information. The mission answered many questions while raising new ones, as successful scientific exploration always does. The spacecraft proved that dedicated missions to Mercury are technically possible and scientifically rewarding, paving the way for future exploration. Rest now and appreciate what human ingenuity accomplished with Messenger, a spacecraft travelling billions of kilometres over nearly 11 years using the gravity of 3 planets to gradually reshape its trajectory, finally entered orbit around a small world hugging close to the Sun. There it studied Mercury in detail never before possible, revealing water ice, magnetic mysteries, and geological features beyond expectation. This is what we can do when we reach for the stars. BepiColombo and the future of exploration. As one chapter of Mercury exploration concluded with Messenger's final plunge, another was already beginning. BepiColombo, a joint mission of the European Space Agency and the Japan Aerospace Exploration Agency, is currently en route to Mercury, carrying advanced instruments designed to build upon and extend Messenger's discoveries. Let us explore this ambitious mission and consider what the future holds for our understanding of the solar system's innermost planet. BepiColombo launched on October 20, 2018 from the Guyana Space Centre in Kourou, French Guiana. The mission carries 2 separate spacecraft that will operate in different orbits around Mercury: the Mercury Planetary Orbiter from ESA and the Mercury Magnetospheric Orbiter from JAXA. Together, these spacecraft will conduct coordinated observations of Mercury's surface, interior, and space environments. Like Messenger before it, BepiColombo must undertake an extended interplanetary journey using gravity assists to gradually reduce its velocity relative to Mercury. The mission's trajectory includes 1 flyby of Earth, 2 flybys of Venus, and 6 flybys of Mercury before the spacecraft finally enters orbit. This complex sequence of gravity assists will deliver BepiColombo to Mercury in late 2025, more than 7 years after launch. The gravity assist flybys provide opportunities for science even before the main mission begins. BepiColombo's instruments have observed Venus and Mercury during close approaches, gathering data that complements the primary mission objectives. These observations have already yielded interesting results, including measurements of Venus's atmosphere and glimpses of Mercury's surface from angles not previously observed. The spacecraft architecture of BepiColombo differs significantly from Messenger's approach. While Messenger was a single spacecraft, BepiColombo consists of 4 modules during cruise: the Mercury Planetary Orbiter, the Mercury Magnetospheric Orbiter, a transfer module providing propulsion and power during the cruise phase, and a sunshield that protects the spacecraft stack from solar heating. Upon arrival at Mercury, the transfer module and sunshield will be jettisoned, and the 2 science orbiters will separate to conduct their respective missions. The Mercury Planetary Orbiter will operate in a relatively low polar orbit that brings it close to Mercury's surface. This spacecraft carries 11 scientific instruments designed to study the planet's surface, interior, and exosphere. High-resolution cameras will map surface features in unprecedented detail. Spectrometers will determine the composition of surface materials across a wide range of wavelengths. A laser altimeter will measure topography with extreme precision. These and other instruments will build upon Messenger's observations while providing new types of measurements. The Mercury Magnetospheric Orbiter will operate in a more elongated orbit that takes it farther from Mercury and deeper into the magnetosphere. This spacecraft carries 5 scientific instruments focused on studying Mercury's magnetic field, magnetosphere, and interactions with the solar wind. Operating simultaneously with the planetary orbiter, It will enable coordinated two-point measurements that can distinguish spatial variations from temporal changes in the magnetosphere. The coordinated operation of two spacecraft offers significant advantages over single spacecraft missions. When the magnetospheric orbiter measures conditions in the distant magnetosphere, the planetary orbiter can simultaneously measure conditions near the planet. This coordination will help scientists understand how the solar wind drives changes in Mercury's magnetosphere and how those changes affect the planet's surface and exosphere. BepiColombo's instruments incorporate technological advances developed since Messenger was designed. Higher resolution cameras will reveal surface details Messenger could not see. More sensitive spectrometers will measure surface composition with improved accuracy. The laser altimeter will map Mercury's topography with finer precision than Messenger achieved. These improvements will refine and extend the database of Mercury observations. Several specific scientific objectives drive BepiColombo's mission design. The mission aims to better understand Mercury's interior structure, including the size and state of the core and the thickness of the mantle and crust. It will investigate the nature and origin of Mercury's magnetic field, including the mechanisms maintaining the dynamo and the reasons for the field's unusual offset. Surface composition and geological history will be mapped in greater detail, addressing questions about Mercury's formation and evolution. The permanently shadowed craters that harbour water ice will receive particular attention. BepiColombo's instruments will study these volatile deposits, determining their distribution, depth, and composition. Understanding how ice survives on Mercury and where it came from will provide insights into the delivery and preservation of volatiles throughout the inner solar system. Beyond BepiColombo, future Mercury missions remain in the conceptual and planning stages. NASA and other space agencies have studied various mission concepts, including landers that would directly sample Mercury's surface and orbiters optimized for particular scientific investigations. The technical challenges of operating on Mercury's surface are substantial, given the extreme temperature variations and intense radiation environment, but such missions are not impossible in principle. A landed mission to Mercury would provide scientific opportunities impossible from orbit. Direct analysis of surface materials could reveal isotopic compositions and mineralogical details that remote sensing cannot determine. Seismometers could probe Mercury's interior structure by detecting vibrations from impacts or internal activity. Heat flow measurements could constrain models of Mercury's thermal evolution. Such a mission would require significant technological development, but would yield transformative scientific returns. Longer-term visions for Mercury exploration have included concepts for human visits, though such missions remain far beyond current capabilities and planning horizons. The harsh conditions on Mercury, including extreme temperatures, intense radiation, and proximity to the Sun, would pose severe challenges for human explorers. However, the permanently shadowed polar craters, with their relatively constant cold temperatures and water ice deposits, might offer somewhat more hospitable conditions for future human presence. The study of Mercury connects to broader questions about planetary science and solar system formation. Mercury represents an end member among terrestrial planets, the smallest, densest, closest to the Sun, and possessing unique orbital and compositional characteristics. Understanding why Mercury differs from Earth, Venus, and Mars helps us understand the processes that create planetary diversity and the conditions that may favour or inhibit habitability on other worlds. Mercury also serves as a natural laboratory for testing fundamental physics. Its proximity to the Sun, where space-time curvature is strongest in our solar system, makes it particularly sensitive to relativistic effects. Precision measurements of Mercury's orbit and rotation can test general relativity with greater accuracy than observations of more distant objects. BepiColombo carries instruments designed to conduct such tests, continuing the tradition begun with observations of Mercury's perihelion precession. The ongoing exploration of Mercury reflects humanity's enduring curiosity about the worlds around us. Each mission builds upon its predecessors, answering old questions while revealing new mysteries. The progression from Mariner 10's 3 flybys to Messenger's 4 years in orbit to BepiColombo's dual spacecraft mission demonstrates increasing sophistication and ambition in how we explore the solar system. As you rest peacefully, imagine BepiColombo cruising through interplanetary space, falling toward its 2025 arrival at Mercury. The spacecraft carries instruments ready to probe secrets that still lie hidden, to map features in detail never before achieved, to answer questions we have asked for decades. The exploration continues, and with it, our understanding of this fascinating world grows ever deeper. Mercury's significance and gentle closing. We have journeyed together through the complete story of Mercury, from ancient mythological associations to cutting-edge space exploration. As our narrative draws to a close, let us reflect on the significance of this small, swift world and what it teaches us about the cosmos and our place within it. Then, as these thoughts settle into peaceful contemplation, allow yourself to drift into restful sleep. Mercury occupies a special position in the architecture of our solar system, representing an extreme among planetary bodies. As the smallest planet, the one orbiting closest to the Sun, the most dense when corrected for gravitational compression, and the possessor of the most eccentric orbit, Mercury marks boundaries in planetary parameter space. Understanding why Mercury exists with these properties helps us understand the range of possibilities for planetary formation and evolution throughout the universe. The study of Mercury has contributed to scientific advances that extend far beyond planetary science itself. The anomalous precession of Mercury's perihelion provided one of the first confirmations of Einstein's general theory of relativity, validating a revolutionary new understanding of gravity and space-time. This single observation from the closest planet to the Sun helped establish a theoretical framework that has guided physics for more than a century, influencing everything from cosmology to the design of GPS satellites. Mercury's geological record preserves evidence of processes that occurred early in solar system history. The heavily cratered terrain records the late heavy bombardment, a period of intense impacts that affected all the inner planets approximately 4 billion years ago. The lobate scarps document global contraction as Mercury's core cooled. The smooth plains record volcanic flooding events. Reading this geological record helps us understand conditions and events from the deep past. The discovery of water ice in Mercury's permanently shadowed craters demonstrates that volatile substances can survive in locations that might seem impossibly hostile. Mercury receives more solar radiation than any other planet, yet its polar craters maintain temperatures cold enough to preserve ice indefinitely. This finding has implications for understanding where water might be found throughout the solar system and how volatiles are distributed among planetary bodies. Mercury's magnetic field, generated by a dynamo in its liquid outer core, tells us that this small world remains internally active after 4.5 billion years. The mechanisms that have kept Mercury's core partially molten challenge simple assumptions about how small planets cool and evolve. Understanding Mercury's thermal history helps us model the evolution of planetary interiors generally. The exploration of Mercury showcases human ingenuity and our capacity to overcome technical challenges. Reaching the innermost planet requires clever trajectory design, using gravity assists from multiple planets to make the journey feasible. Operating spacecraft in Mercury's harsh environment demands innovative engineering solutions. The success of Mariner 10, Messenger, and soon BepiColombo demonstrates that we can extend our reach into even the most demanding regions of the solar system. Mercury also reminds us of the diversity that exists among worlds. Even within our own solar system, planets vary enormously in their properties and environments. Earth's comfortable conditions for life are not replicated anywhere else that we know of. Mercury's extremes of temperature, its lack of atmosphere, its ancient cratered surface, all stand in stark contrast to our home world. Yet Mercury and Earth formed from the same primordial nebula, siblings born from the same cosmic parent. The cultural history of Mercury connects us to our ancestors, who gazed upon the same celestial body thousands of years ago. When we observe Mercury's transit across the Sun, or catch a glimpse of the planet in twilight, we participate in a tradition of sky watching that extends back to the dawn of civilization. The mythological associations, the astronomical observations, the scientific discoveries, all form a continuous thread of human engagement with this wandering light in our sky. As you reflect on all we have explored together, allow a sense of wonder to settle over you. The universe contains countless marvels, and Mercury is among them. This small world racing around our sun, bearing the scars of ancient impacts, hiding ice in shadowed craters, generating a magnetic field from its still liquid core, has revealed secrets to patient investigation while keeping others yet undisclosed. Future missions will uncover more, and the story of Mercury will continue to unfold. Now let the detailed facts and figures fade from conscious attention. Let the names of spacecraft and the values of orbital parameters drift away. What remains is a sense of connection to something vast and ancient, a feeling of participation in the grand project of understanding our cosmos. Mercury has been our companion through this journey, a window into the workings of the solar system. The night surrounds you now, peaceful and still. Somewhere above, if you could see it, Mercury traces its swift path around the Sun, just as it has done for billions of years. The planet does not know we have studied it, does not care that we have sent our robotic emissaries to orbit it and map its surface. Yet our understanding enriches us, expanding our conception of what exists and how the universe operates. Breathe slowly and let relaxation deepen. The story has been told, the journey completed. Mercury has shared its secrets, and we have listened. Now it is time for rest, for sleep, for the restorative quiet of night. The cosmos will still be there when you wake, with all its wonders waiting to be explored further. Let your thoughts become soft and diffuse, like starlight scattered by atmosphere. Mercury orbits on, indifferent to our sleep or wakefulness, following the laws of physics that govern all celestial motion. And you rest, a conscious being in this vast universe, having spent time contemplating one of the countless worlds that populate the cosmos. Sleep approaches now, as inevitable as Mercury's next orbit. Welcome it. Let consciousness fade gently into dreams. Perhaps Mercury will appear in your dreams, its grey cratered surface stretching to horizons beneath an enormous sun. Perhaps you will drift among the stars, weightless and free, observing the solar system from perspectives no human has ever occupied in reality. Whatever dreams may come, they will arise from a mind enriched by knowledge of Mercury and its place in our solar system. The story you have heard will become part of you, available to recall whenever you think of the swift messenger planet that never strays far from the sun. Rest well. When you wake, the universe will still hold mysteries enough to fill 1,000 lifetimes of exploration. Mercury will continue its rapid orbit. BepiColombo will continue its patient approach, and human curiosity will continue seeking understanding. For now, though, sleep is the destination, and you have arrived. Thank you for joining this journey through Mercury's complete story. If you have enjoyed this exploration, please consider liking this video and subscribing to the channel for more cosmic adventures. Every like and subscription helps bring more content like this to viewers who share a love of space and science. Until next time, sweet dreams and peaceful sleep beneath the stars.